Okay, in the last segment, we motivated the Huffman coding algorithm, and the greedy choice it was going to make was to take the two symbols of least frequency and combine them into one symbol, one fake symbol of frequency, the sum of the two symbols. Let's see this algorithm in action on an example, and then we will see why it is correct. So let's take this very simple example. There are four symbols. A has frequency 0.3, B has frequency 0.25, C has frequency 0.25, and D has frequency 0.2. Frequencies or probabilities, however you want to think of them. These sum to 1. So what we will do is we notice that C and D are the two lowest frequency symbols, although there's a tie between C and B for the second lowest. That's all right. We'll treat C and D as the two lowest frequency symbols, combine them into one symbol Z, which now has frequency equal to the sum of the frequencies of C and D, which is 0.45. So we now have a problem on three symbols, A, B, and Z, as shown here. So we compute the best tree on A, B, and Z. Again, what would we do there? Huffman's algorithm would say combine the two symbols with least frequency, which are A and B now, make them into one, and that new symbol has frequency 0.55, the sum of these two. So that one symbol has frequency 0.55. But after we do that, we are down to two symbols, Z and this new symbol that is a combination of A and B. Let's call that new symbol Z prime. When we're down to two symbols, Z prime and Z, we know the answer. Whenever we're down to two symbols, the tree is obvious. You just start with the root, give it two children, make one symbol 0 and the other symbol 1. So maybe we made Z prime 0 and Z 1. So this is 0 and this is 1. Now we got to unravel what we did and compute the original solution again. Z prime was the result of combining A and B. So we take Z prime and we replace it by actually A and B here. So A is now encoded as 0, 0. B is encoded as 0, 1. Similarly, Z was the result of combining C and D. So we now replace Z, as shown in this picture here. We replace Z with the subtree consisting of C and D hanging below it. And now we have the entire solution. It turns out that for this particular case, the best answer is a tree where all the leaves are at the same depth of 2 here. All leaves are the depth 2. And so this is a kind of a boring code. Every symbol has a two-symbol code, 2-bit code. This will not always be the case, but in this case, this example, that's what happens. But I hope the working of the algorithm is clear to you from this very small example. We repeatedly combine two symbols, replace them by a fake symbol, a new fake symbol every time, until we get down to just two symbols, at which point we build the tree trivially, and then we unravel all the combinations we did in the reverse order in which we combined them. So here is another example with 5 symbols this time, A, B, C, D, E. And you can see the frequencies. A is much more frequent than any of the other symbols. Well, going back again, so D and E are the least frequent symbols, so we combine them to create a new symbol, Z1, that represents their combination and has frequency 0.275, the sum of the frequencies of D and E. The two lowest frequency symbols now are B and C, so we combine them. So we combine B and C and create a new symbol, Z2, for the combination, which has frequency equal to the sum of those two, which amounts to 0.325. Now the two least frequent symbols are Z2 and Z1. Notice that A is still higher frequency than either of these two. So we combine Z2 and Z1 to make a new symbol, Z3, which has frequency equal to the sum of those two, which is 0.6, and we are down to two symbols, A and Z3. At this point, we build the tree trivially as just that. So A gets the symbol 0, the bit 0, and Z3 gets the bit 1 as its encoding. And after we've done this combination, we unravel the combinations we did. Z3 was obtained by combining Z1 and Z2. So we make Z1 and Z2 hang off Z3. Z1 was created by combining D and E, and we hang D and E off Z1 and so on. So that's how you build a tree in this slightly bigger example. Now we ask ourselves, why is this algorithm correct? Which is a question we have to always ask ourselves. If there's one thing you learn from this course, it's the idea that when you design complex algorithms, it's not enough to just say, this feels right to me, let me write my code this way. You've got to ask the further question, why is what I did correct? And that's what we will reason about, at least informally in this case. A few points I want to make before I plunge into this somewhat complicated proof. One thing to note is that, as we said in the beginning, any prefix code can be represented as a binary tree. In a binary tree, the nodes at the very bottom, which don't have any children below them, are called leaves, as you've seen before. So this may be a binary tree, and the nodes at the very bottom are called leaves, right? So this is a leaf. This is not a leaf. This is a leaf, and this is a leaf. The nodes at the bottom are called leaves. The nodes that are not leaves are called internal nodes. This is an internal node. So this is an internal node. And so every node in the tree is either an internal node or a leaf. The root is an internal node, and other nodes are internal nodes. Now, you can see that in an optimal Huffman coding tree, you should never have an internal node that has only one child. Every internal node must have two children. Why is that? Well, if you had an internal node with just one child, so imagine for a moment that in this tree, this was an internal node, this is an internal node, so it didn't have this child here. So what could happen? We could actually take the entire tree that hangs off the other child and move everybody up one level. And that would just reduce the code length of many different symbols in this tree, thereby reducing the overall code size, average code size. So when you have an internal node with only one child, that's not optimal because you can migrate up everything that hangs off the one child. And so every internal node in an optimal tree must have two children. Okay, so bear that in mind. Now, if you think about a binary tree where every internal node has two children, there have got to be two leaves that hang off at the deepest level. At the deepest level, there must be at least two leaves that both have the same parent. So we argued that every internal node must have two children. So in fact, at the very bottom of the tree, there must be an internal node which has two children which are both leaves. And these are the deepest leaves in the tree. This picture must exist. The rest of the tree is somewhere above, but this picture must exist at the very bottom. We call these two leaves here sibling leaves because they have the same parent. Following sort of what we would do with human families, these are called sibling leaves. Two people with the same parent are called siblings. And so these two leaves are called siblings. And we saw that the algorithm puts symbols with the lowest frequencies in sibling leaves because it combines the two symbols with the lowest frequencies into one. And when it finishes, it finally uncombines them and puts them as sibling leaves. So why is that a good idea? So in fact, we can also see, and this requires a little bit more of a proof, that the two symbols with lowest frequency are not only going to be sibling leaves, they're going to be sibling leaves at the deepest level. I won't prove that here. So the reason why this is good is basically exactly the exchange property. This greedy choice is a good idea because of the exchange property. If you had another algorithm, an optimal algorithm, that put a symbol with greater frequency at the lowest leaf, then you could exchange it with the symbol with the lower frequency and get a better code. So we will see this example in the next slide. So essentially the idea is that the optimal tree existed with higher frequency symbols at the deepest level. We could swap the lowest frequency symbol with one of the deepest ones and get a tree with lower cost. This is a contradiction since we started by saying the tree was optimal. So look at the previous example where the frequency of the symbol A is 0.4, but the frequency of D is only 0.15. A is a very frequent symbol. D is a much less frequent symbol. And supposing the Huffman code had produced, the Huffman algorithm had produced, or some algorithm produced a tree that looks like this. So that the code word for A has length 3, whereas the code word for D has length 1. Then what we can do is we can exchange the positions of D and A in the tree and get a much better code. So imagine that the file you're transmitting is this file here, AAD, 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 etc. That's the beginning of the file. So if you have the file AAD, 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 AA, then if you exchanged A and D, then you get this encoding, which looks kind of long. But if you actually kept A, you put back D at the bottom and A at the top, then you get a much shorter encoding, which we will see as looking like this. Okay, that's just a proof by example. This is not a real proof of the correctness of Huffman. To prove it correct, we would actually have to argue a little bit more about why the exchange property works and why the lowest frequency symbols will end up at the deepest levels of the tree by Huffman algorithm. The entire proof is something I'll leave you to think about, but at least I hope I give you an intuitive idea of why Huffman's algorithm is correct.